Welcome everyone for this session today. I'm very excited to have our principal solution architect Neil Stevenson on this campaign in December, and we're going to talk in more details about best practices for using Hazelcast. So, good morning, Neil. How's it going?
Good morning, Floz. Things are going well. Things are going well. We're all set for today. So it's been a lot of work in the preparation, but yeah, we're good to go.
So it took us some time to get here actually, and we started with a specific number, and this number, start to increase. And so I'm very excited to actually go through these best practices. So for anyone listening to us today, or watching us in recording mode, I encourage you to watch towards the end because there are more towards the end for best practices of using Hazelcast. So there is a basically benefits from each use cases. But before we started, perhaps we talk a little bit about you and your experience with Hazelcast over 10 years. So that's really
Yes.
long
So
time.
I've been working with Hazelcast for, yes, very long time. And I've seen the product evolve, and I've seen various things that people have done with it, including various things that people have done wrong. This is not what we want. We want your Hazelcast to go well, and that's the whole point of these things, is kind of find out what the best practices are. And when we kind of first came up with this idea, I thought, well, it's what the 10 things, and it's slightly more than 10, but it's not 10,000. So and we'll put them in order as well. So if you're watching this video and you kind of get halfway through, then you pick the most important half rather than the least important. But please watch to the end.
Yeah. Yeah, I think this is important. I think because going through these use cases, it varies. Obviously, I don't want to reveal it now, so we'll leave it. So when I joined Hazelcast, like about, I would say, is it 18 months now? I forgot.
Yeah,
But
time is going by.
Neil was my boss when I joined, and there is so much you can learn from Neil. And we also always say speed matters. You're as well a runner. So how's running going?
Oh, running's not well. It's cold where we are currently, so I'm not a great fan of running outdoors when it's cold. I'm treadmill, so running not going so good. But paused over the winter perhaps is um, more of an indoor thing for me right now. That is. So.
Yeah, that's great. So shall we get going? Because there is lots to go through today. So do you want to start? And then we can pause after each golden rule to get some questions.
Okay, let's start screen sharing. Just need this to go. So, best practices. Best practices. We've been working on this for a while. We kind of finished this in October. Been circulated a few people, and now we want to do like a video version to go through what these best practices are about. The current version of Hazelcast today is version 5.3, version 5.3.6. But these practices are also valid for 5.4 because we know what's in 5.4. And in the future, later versions of Hazelcast, most of them will probably still apply. So let's kind of move on. Best practices. Where did we come out for this? And it's obvious we want your Hazelcast to go well. That's good for everybody. And part of this is, well, what does good mean? And these are, think of them as guidelines rather than rules. You don't have to follow them. What's important, and this is why it's a video, is we're going to explain them so that you can understand them. Because if you understand them, then you can choose to follow or you can choose to ignore them. So, if I was to give you an example, don't run with scissors. is, that's maybe a best practice for life, but you can choose to run with scissors because once you know what the risk is. And you could run a marathon with a pair of scissors and not fall over and think you've done it right. And maybe you have, maybe you've not. If you spoke to a first aider, they'd tell you a different perspective. They've seen everything that's going wrong repeatedly. And that's where don't run the scissors is what they say. Maybe you don't fall very often, but when you do, So this is kind of where we're coming from with these best practices, things we've seen that people have done wrong and things we've seen that people didn't really understand what it was for. So how many? Well, we originally started with 10. We're now up at 14. As I mentioned at the start, we'll kind of cover them in what we think is probably the most important order. So follow them all if you can. If you just do the first ones, then hopefully they're the more important ones to you. So 14 guidelines. The 14 things we're saying, you should understand this and things will go well for you. It's not everything. It's not everything, we can't do it. Look, don't run with scissors. I've even put it in writing, that's maybe the question is, in fact, don't run with scissors. What we're actually saying is don't fall, So how it's expressed and what the meaning is kind of what these rules are about. And just get in here at the start. Don't forget rule 2. We haven't told you what rule 2 is yet, so here we go. So rule number 1 is about serialization, which is for us kind of one of the most important things that's going to affect the performance of your Hazelcast cluster and a few other factors around it. So Hazelcast is a distributed system. Typically, it's a cluster of multiple processes, typically across multiple machines. And that means moving data from place to place. So what's important is that movement of data from place to place happens quickly. Speed matters. What we're thinking about here is how is data written? How is it read? Where does it go from place to place? Because in Hazelcast, you typically have backups. So if you write a piece of data to one process, it's backed up to another process. So you write it to one, that's one network transfer. It gets sent to the backup. That's another network transfer. You might have persistence on if you're using the commercial edition, which is up and down to the disk. We might rearrange data if your cluster changes size. It can move about a very large amount of the time. So that's important to understand really how much your data moves. And to understand this, we're actually going to, a lot of these examples are Java, because Java runs on the server side. Hazelcast is fundamentally a Java-based server process. And if we are doing, the classic put on hello world into a Hazelcast map, then hello is the key and world is the value. So that string hello, you have to serialize, turn it into a flat series of bytes to transmit across the network. You might look at it and think, well, a string is a flat series of bytes already. And it's like, yes, it is, but it's not a byte array, so it isn't particularly difficult to flatten. So you've got to serialize the key to send it to the server. You've got to serialize the value to send it to the server. The way Java map definition works is it returns you the previous value when you do a map insert. So that has to come across the network. So there's at least 3 things that are going on. You've got to serialize the value you're sending, serialize the key you're sending, and deserialize the old value you get back. And potentially there's stuff going on the server side as well, depending whether you've dictated that the value is stored serialized or deserialized. So if you say store it serialized, it arrives serialized, you don't have to do anything. If you say store it deserialized, it arrives serialized and has to be deserialized. And lots of work going on in terms of network transfer and computation to do the serialization, deserialization. Now, for a word like hello, it's not a lot of computation, but it's not zero. So this is where it all gets a little bit messy, which is why this is probably the most important thing. There are 5 kind of considerations, and we're going to run through them all. And there's 5 factors that you need to think about in terms of serialization, and 3 ways you can really go about it. But you have to remember pragmatically, this really matters for data that you're using all the time. There's some data that might sit in Hazelcast and you don't use it particularly frequently. So is that worth serialization improvements? Well, maybe. It's all about return on effort. If you put in some effort to optimize something that doesn't get used very often, what's the point of that? So we're going to run through the considerations. Interoperability. So I just said you put data in a Java store. Well, can you get it out from Node.js? Yes or no? Well, if you put it in a Java-only format, then a non-Java program can't read it. If you put it in an interoperable format, then a non-Java program can read it. So you've got to kind of know, first off, what's the kind of long-term future for your application? Are you going to have clients in different languages accessing your data? Because if you do, then that just automatically rules out all the Java specific. And this is quite important to understand, because where most people start with Hazelcast is they have like an existing application and they add Hazelcast to it. And then as it starts to become more useful to them, that's when they start having other clients. So you might kind of start and say, well, no, we're a Java shop. And then over time, well, actually the .NET team want to have a piece of this as well because it's so good. So it's really about the long-term future. You'll know whether or not other languages are likely to feature. Money. Serialization. If you serialize an object, you're flattening it down, and how you flatten it out might be different sizes depending on the different algorithms. So that's going to cost you. So simplistically, if it compresses to a small size, then it's not going to cost as much money. But that's about, perhaps it's about hardware, because you need the machines. Perhaps it's about cloud costs because you're moving data across the network, and that's what you can be charged for. So price, money. And again, you maybe don't worry so much about it if you've got very small amounts of data. Once the data gets large, then the kind of size of each data packet mounts up. After money comes speed. This is what we're all about. Your size of your data is going to affect how it moves across the network, but not kind of in a linear way, because network transfer moves in a buffer. So if your buffer is 1,500 bytes and your data object is 1,400 bytes, it fits in the buffer, and that's one network hop. If you make it just a little bit bigger, so it's gone from 1,400 bytes to 1,600 bytes, that's not a massive change. I can't even work out what that is in percentage terms, maybe about 15% or so. It's got a little bit bigger, but now it's 2 network blocks, so the network time is considerably larger. So just that little tweaking of the size of the object, if you don't have your network tuned, then the object size, the serialization is one thing, but the transmission time could be significantly different just for a tiny little change in the object structure. Maybe the answer to that is you want to tune your network buffers, but you don't always have access to that. But transmission time is fundamentally to do with the size of the object, but it's not linear. 5% bigger does not mean 5% longer necessarily. So continuing with time, I mentioned about the you've got to serialize it. You take the structure it's in and you convert it to a flattened format to send across the network. And then when you receive it, you kind of deflatten it and rehydrate it, whatever you want to call it, turn it back into a structured object. And that's going to take time. And some algorithms are faster than others. And this is also like a trade-off. If you kind of do like a lot of compression, that's a lot of CPU, and then you get a small data object. So you win with one and you lose with the other. So you've got to be careful, don't obsess about compression. But maybe that's a good choice. If it's data that's huge and you don't access very frequently, then the kind of compression time isn't relevant and the storage cost is relevant. This is all about just kind of understanding what matters. And all of these, as you explain them, they say, that's obvious, isn't it? And this is why we get them in, because they're only obvious once somebody's told you. And the last one, let's all imagine we've won our country's lottery and somebody else has got to pick up your code and they've got to figure out what your code has done. So if you've coded the serialization logic, somebody's got to pick this up and run with it, run with the scissors that you've made. They've got to do that serialization, any tweaks if the data model changes. If you write that code, you've got to maintain it, or somebody else has got to maintain it, testing and all the usual kind of stuff. There are third-party serialization libraries, and if you look at library, you've got the current version is 2.5.4. Well, something was wrong with 2.5.3. It's just somebody else has developed it. Doesn't mean it's perfect. But if it's like a common library, then faults get spotted quicker than a rare library. So maybe not a bad idea. So let's, now we've got those 5 kind of considerations. Let's just run through the 3 choices. So style 1, Java standard. Forget about this entirely if you're not going to be using Java and not going to be using only Java. And basically, this isn't, Java standard doesn't perform well. We've got some numbers we'll come to in a minute, but Java's serializable. It's okay. It's very slow, but you only write 1 line of code. You just do implement serializable and you're done, and Java figures out the rest. So it's slow, but it's like pretty lightweight from a development perspective. So, the technical debt on that is very low. The considerations about the CPU and the transfer time, it's going to be bad for that. So if that is relevant because it's an object that's used frequently, then this isn't a good choice. There's another Java standard way called externalizable. Forget about it, because if you're going to write the code, there's better ways. Which comes to better ways, number 2. So, this has been a thing we've had in Hazelcast for a long time, ways to improve serialization. So, one of the original ones was a thing called data serializable, which is like a Hazelcast tweaked version of Java's externalizable, what I mentioned on the previous slide. Don't use identified data serializable is actually a better thing, and that's the one we use ourselves for all the kind of metadata in Hazelcast. So it's a good choice. You've got to write coding. So that's the technical debt, but what it produces is quite compact. We have a couple of other versions, and we've actually highlighted them as don't use and could use. And these are guidances. If your system is using them, that's not a problem. We're just saying, well, we've thought of a better way to do this. So the portable and version of portable is okay. It's interoperable. It works from other languages, but it's actually been superseded by the next one down, which is this thing called the generic record, where what will happen behind the scenes is Hazelcast will figure out the structure of your data object for you in a similar kind of manner to Java's reflection, but do it much more efficiently because of Hazelcast-based optimizations. So you can create an object and just shove it into Hazelcast, start querying it, and the object structure is deduced for you. So it's not a bad choice. You know, you've got no technical debt because you're not writing code. It's compact, as the name suggests. So it's really not at all a bad choice. Or you might go for something like JSON down at the bottom. I quite like JSON. JSON is like a free-for-all in terms of object structure. So maybe that is the choice. Do you want like a loosely typed object where you can just add fields, take them away, have two objects that don't have the same fields? That's the great plus, or the great minus for JSON is just this looseness of approach. And you know, there are no wrong answers here. These are all fine. We're just saying, well, if you were going to start, don't bother starting with data serializable. You should use identified data serializable. Well, one's a better version of the other. If you've already started and you've got that, that's fine. And then the last of the three ways is, you know, so the first way was the Java standard ones, and here there's some Hazelcast ones, and you might just say, well, I'm not going to write the code, and I don't like the default Java ones. I'll just use a library. And that's a great answer as well. And there's, you know, a number of libraries out there. There's a few listed here, and I'm sure you can work out what ones you like. You know, they're generally pretty easy to work with. You know, and you know, this is what they're for, so they do a good job in terms of compressing and decompressing objects. One little gotcha there, just always be careful on the licensing of a third-party product that you then use in your software product, because if you might not be able to use your software product in certain ways because of license restrictions. So one, double check. It's a thing that often gets kind of forgotten about, and then once it's found, that's a big problem to sort out. So those are the kind of three. We said about some numbers, and 10 times is really the only thing you've got to remember. You know, this was just some experiments we did with some data. Your data is going to be different, so your numbers are going to be different. But we serialized an object using Java standard, Java IO serializable, and it came out at 400 bytes. I forget which one was the more compact. I think it was, in this case, it was the JSON one. Go JSON. And it came out about 40 bytes. So it's like a tenth of the size. And again, in terms of serialization, I think we serialized 100,000 objects, and it took 11 milliseconds with the Java standard one, because it's doing reflection. It's looking into the object structure, and versus 1.3. So it's 10 times bigger or 10 times faster. The worst is always Java serializable, but remember, it's only worst in terms of performance. In terms of coding, it's just one line, you know. So for data you don't have a lot of, or don't care about the performance of, it's not a bad choice. Best, that's a bit harder to determine, because that really very much depends. I like JSON. I've mentioned it twice and given it a thumbs up on the video, but that's just me. And you might prefer, in this case, protobuf or whatever library you think is great. You know, they all perform well. All the third-party ones, it's the whole reason they're there. So they all do a good job at that. So best will be, and perhaps the answer there is, because they're all about the same, well, just pick your favorite then. Don't try and get to perfection, because you'll maybe never get to perfection, but get 90% perfection or 99% perfection. So that's serialization. So just to summarize, the reason this is our most important one is because it's going to affect you in terms of performance, and it's going to affect you in terms of money. Data is moving about all the time, so that is going to affect the performance of your application. It may affect your billing because of your network and the amount of data. If it's 10 times bigger, you're going to need 10 times more machines, and machines aren't free. So that's kind of why we kind of really, really want to stress rule number one is the most important, because performance and money. So there's our summary. The data moves all over the place. because you're pushing it in and out the system, because it doesn't generally have a lot of value just sitting there and idle. So just to remember, and just to kind of recap, technical debt, who's going to run this if you've picked a complicated way to do it? But, as I said, if you win the lottery and you're gone, it's not your worry, but, it's somebody's worry, and you should really be much more diligent. Say, well, look, doing a proper job on the system means consideration on the long-term maintenance, consideration on the cost, as I mentioned, and that capacity thing. So it's all about the kind of bigger picture. And kind of the reason we want to get this across so much is, if you're doing a coding thing, it's very difficult to change once you've done it. So you kind of got to know the right answer before you begin. It's not like an easy thing. So that's why the kind of no-code versions are quite good. Anything where you don't have to write code means you don't have to rewrite code if you don't have enough hardware for your data. We need to compress it. Oh, I've got to change the code. No, so not popular. So that's rule number one. Rule number one is very important. So rule number two is the second most important thing from Hazelcast. And rule number two is, don't forget rule number one. We can't make it any simpler than that. This is, okay, there's a little bit of jocularity here. This rule number two is irrelevant, but it's really rule number one. Just getting another mention. There was a quote from a very famous rich person. His rule was like, don't lose money. It was the most important to him. And serialization, well, certainly for me, is quite an important consideration. So that was number two. Number two and number one, you should hopefully have embedded in your head by now. Do we even summarize it? Yeah, we do. Don't forget rule number one. So rule number three, this is one, and this is quite important too, because this costs a lot of money for people in rework. Plan security first. And the reason for this, fairly typically in a project, security is kind of one of the last things you do because, it's a non-functional, and they're always kind of done towards the end, because you've got to get the functionals working before, you can't performance test it till it's written. So the non-functionals are always done towards the end. And, this data you're putting in Hazelcast, it's, business data, you're probably going to want to secure it. And if you do, and you do that at the end of the life cycle, you might have to do some rework. And that is not going to be good if, you're 2 weeks from going live, you do a review that says we've got to introduce security, and that means you've got to do some recoding. Nobody's going to like that. So there's nothing wrong with doing the security at the end. What's wrong is not to think about it until the end. So just have it in mind that your data may be secured. That is really the rule. It's not particularly great fun for most people to have security. It just stops you connecting, but that's really what it's for. That's why security is about. Stop people accidentally accessing or deliberately accessing your vital business data. I mean, who knows what's in there? It could be, personal information, credit cards, all sorts of stuff in your Hazelcast cluster. And where it's important is security will change a number of things. The first is, as I mentioned, Hazelcast often starts with like an embedded application. So you've got an application, you have a Hazelcast server inside it. And if you've got a Hazelcast server, then security is compromised. How can you protect the data? Well, the API stops you accessing the data, but if you're running in the same process, you can just look in the process's memory. So, the security in that sense requires client server. So you are a process, you make a network call to the server, passing it your credentials and say, I'd like this piece of data, and it maybe does or maybe doesn't, depending on your credentials and your role and all that kind of stuff. So if you implement security, you need to be client-server. So if this is the last thing you've thought about, you're just about 2 weeks from going live and you need to change your architecture, that's a disastrous amount of rework. So that's the thing, maybe to think, security only works across a network protocol. You're saying, give me this data and you cannot bypass the mechanism. Can't cheat and look in memory directly. So if you change in your architecture, that's a big thing to do at the end. Nobody's going to like that. Second thing to think about, performance. If you're encrypting your data, that's a further transformation, not a lot different in terms of like how you think of serialization. You take the object, you transform it into a different format. So that is a CPU cost. Not much CPU cost, but it does depend on what your security encryption library is. And, we've seen it, kind of generally it's low percentages, 1 or 2% maybe, but we have seen high, like 10% or so. And it's like, wow, that would be not good if you're a performance critical application. And obviously that's taken up your CPUs, which is back to serialization. And you're going to need more CPUs and they're not free. So, think about that to begin with. More on performance. So with Hazelcast, so there's authorization, authentication, and encryption. We just covered the encryption. So when a client connects, it is authenticated, meaning you're passing your credentials to your server saying, I'm Neil, can I connect, please? And those credentials get validated against somewhere in LDAP server, Active Directory, and that's not an instant process, but that's not really that much of a problem because typically a client starts, connects to Hazelcast and stays connected for a day, a week, a month, whatever. So that one-off connection cost isn't particularly bad. But if you've got a client that starts, connects and shuts down, starts, connects and shuts down, then that whole authentication piece will be relatively large. And the other part of security is authorization. So I say, give me this piece of data, please, or change this piece of data, please. And it's please, and it may be declined because the operations are validated. So if I'm doing, my code could do insert row 1 and insert row 2. So that's 2 inserts to be authorized. Can I do an insert? Can I do an insert? Validated twice. If I did a bulk insert, here are all these rows, please insert them, then that is validated once. So a little bit more efficient. And again, for high-speed operations, that's a thing you should be doing anyway. So block puts are faster than individual puts in a loop. Who knew that? It's obvious, but these are why we state them, because, oh, yeah, that actually, yeah, that's important. And this code now doesn't work. So you've done something like a map put because you're familiar with a map and or a map get, say, and your coding is this entry in Hazelcast, and yes, it is, or no, it isn't. And you've got an if statement, and then you do your security, and now you've got 3 results to deal with. You've got yes, it is, no, it isn't, and I'm not telling you. It is security exception. So you've got exception handling. So your code logic has now got 3 outcomes to consider, or an exception handler where previously it didn't have an exception possible. So if security is added, that code changes. And the thing about security being added is that often is forced upon you. Somebody says, look, we've got to secure this data. This is important to us. So it doesn't matter when you add security. What matters is when you think about it. Think about security early. because you might need to be client server. It's going to affect your performance and therefore maybe your infrastructure, and it's going to affect your coding. So those are all things you have to bear in mind, so that you can add it in towards the end, or add it in at the start would be nice, but our experience is most usually it's added in at the end. So that's number 3. So rule number 4 is around failure. It's going to happen. Did we say Hazelcast is a distributed system? It runs across multiple machines. So there's all sorts of things that can go wrong. You've got Java virtual machines, you maybe got virtual machines, you've got hosts, networks, PSUs, power supply units. Power can fail. For us, we're going to blame the power. So today we're going to say that the power's gone. There's a power cut, or somebody's pulled the plug out on a server, because it's a lot nicer to kind of imagine that kind of scenario than say, JVM crashed or something. That's not too keen on that one. So the thing is like, well, there's lots of bits, they can all fail, and you can't stop it. If you've got multiple machines, you just got to say, well, yeah, we've got lots. Let's give us your worst. So yeah, hardware. So there's a thing I read, mean time between failure of 1,000 days is like typical for a kind of reasonable spec machine. So if you've got 140 Hazelcast instances, then that's going to mean one machine failing every week. If I've done those numbers correctly, and if it's a 3-node cluster much smaller, then you're going to have a machine failing every year. So 1,000 days is about 3 years. So if you've got 3 of them, that's one a year. If they all take their turn, one fails in the first year, one fails in the second year, one fails in the third year. Might not happen that way, but let's go with it. So you're going to have a machine failing. Presumably your Hazelcast cluster is going to be running in production for more than a year. So it's going to see a failure. I've covered this a little bit because I can't remember all the exact slides in order, but that's it. Think of it like this, but think of it in terms of capacity. So if that 140 node Hazelcast cluster, you've lost one because failure, well, you've gone to 139. And apparently that's 0.7% of a deviation. So your cluster is going to run 0.7% slower. And if that's, your e-commerce website, that's perhaps imperceptible to the user. Nobody's going to know. Whereas if it's a 3-node cluster and you lose one, it's now a 2-node cluster. So that's a massive drop in terms of capacity of 33%. It's going to run considerably slower, or it might not even run fast enough, depending on what your SLAs are. So we'll come to that. So Hazelcast is designed for this. This is what we do. When the going gets tough, the tough get Hazelcast. But it's not indestructible. You can lose a node. You can maybe lose 2 nodes. You can't. What happens if you lose them all? So you can lose a node if you had that 140 or whatever number you happen to have of Hazelcast. There's considerations around processing speed and data loss. So we mentioned earlier that you write a data record into Hazelcast. The default backup count is 1, so there is 1 backup. So that data record goes into one server process, one server node, and there's a backup copy in another server node. So you've essentially got a primary and a backup. You've got 2 copies in total. You can lose either one of them and not lose that data record. So if you lose one node, you've lost 1 over nth of your capacity, but you haven't lost any data if you've got backup count 1. If you had backup count 2, you can lose 2 nodes and not lose data. If you have backup count 3, you've got 3 nodes and not lose data. At some point, if you lost 10 nodes or 20 nodes out of your cluster, you're going to start losing data because you've lost more machines than you have data copies, your backups. But that's thinking of the problem the wrong way. It's like, are they all going to fail? Well, it can happen, but it's all about balancing probability. Is one machine going to fail? Absolutely guaranteed, because it happens. What about two at the same time? And it's like, what's the mean time between failure? 1 in 1,000 days. So that's 1 in 1,000 times 1 in 1,000. That's now a 1 in a million shot. So two failing for unconnected reasons, unconnected being the kind of key word here, seems pretty unlikely. You might have one that you've taken down for maintenance and another one fails at the same point in time. Oh, it's not been a good day for you. But two breaking at the same time for different reasons, unlikely. Two breaking for a related reason, if there's a flood in the data center, well, all the machines are going to be affected. So you could lose a lot. So you have to consider that. So generally kind of what we're saying is one is definitely going to fail. Two, if you're unlucky, and all of them if you're very unlucky. But the kind of in between kind of concepts, are 5 machines going to fail and you've still got the 135 because you're that 140 node cluster? Doesn't seem very likely statistically, for unrelated reasons. If all those 5 machines are in the one stack and the power cable gets pulled out, all 5 will go. So you would want 5 power cables. But you're probably not going to have 5 power cables. And these are the things you've got to kind of understand is what's the trade-off on the infrastructure. 5 power cables is no good unless you have 5 power supplies, 5 power sockets, and, it starts to get very expensive. So you've got to think of it a different way that, yeah, just let it fail. So let it fail. At some point, that bad action is going to happen. You can lose a machine, you can lose 2 machines. Once you start thinking, 4 machines have failed, what kind of hardware have you bought? You bought rubbish hardware, so that's the wrong solution. Buy decent hardware, then 2 machines failing, 3 machines failing. Once you're up at 4 or 5 machines failing, that's pretty unlikely. But there is definitely that case where they all go because the data center catches fire or floods or whatever sort of catastrophe happens. And that's where you kind of need to think of a DR solution. And that's not Hazelcast. All your business is using one data center, and that data center catches fire, that's your business. So you have 2 data centers or 3 data centers or however many you have, and you need a data sharing solution, which Hazelcast can do. So in terms of planning for failure, you've got to work out what you need to make everybody happy. And this is smaller than the cluster size. So what you've got to do is, how much data have you got? Let's say you've got, I don't know, pick a number, a couple of hundred, half a terabyte. So how many machines do we need to store that? And that's a certain number. Let's just say 10. So you've got 10 machines to store the data. How many machines do you need to meet your compute load? And maybe that's 12. So you need 10 for storage, but actually 12 for processing. So that's a 12 node cluster. Or maybe you only need 8 for processing, but it needs to be 10 for storage. So whichever is the larger number, is the winner here. So you need 10 nodes to hit your SLAs. Or if your data is quite small and you come out with 2, no, it's 3. Always go with at least 3. That's one of the things we've seen people go wrong. They try and do, we just need 2 nodes. And it's like, no, you don't. It's a very bad number. 3, or in this case, I've said 10. So I need 10 to be happy. And then I want to be happy on the bad day. I've taken a machine down for maintenance and another one has crashed. I need still to have 10. And that means I need 12 as my normal cluster size so that my impaired cluster size of 10 still hits my SLAs. I'm saying that I think I will tolerate 2 machines failing, because that's that 1 in a million chance, or it's 1 in 1,000 when I've taken one offline for maintenance, that another one goes off the line. I'm not expecting in my setup 3 machines to fail or 4 machines to fail. On those days, if that happens, well, something's really gone wrong in terms of my planning, and I'm now down at 8 because I've had a 12 node cluster because I thought that was the right size. Somehow 4 have failed. Now I'm at an 8 node cluster. I'm below my SLAs. That's bad. But it would still run, but now we've maybe lost data, as we mentioned, because of the number of data copies. If I only had 1 copy of my data, then the 2 machines that failed might be the 2 that have the data record and its backup. So there's a minimum viable size, that's it. And then you add on your tolerance, and that's your number, that's your cluster size. So think of it, your cluster size when you're unhappy, you add some more, and that's your cluster size when you're happy. And it's really not, difficult when you think of it that way. But what we see a lot is people will say, well, yeah, we need 3 to run. And it's like, we've done the numbers. And it's like, no, you need 4 to run. You need 3 to run impaired, is the way to see it. 3 is always the minimum. Never go less than 3. Because we don't even support that below less than 3. We've just seen it go wrong all the time. Rule number 5, network speed, and you won't get that network speed. And if you remember, rule number 1, Hazelcast is a distributed system. We're running data, we're moving data all the time. So when you do a read, you retrieve it from where it is. When you do a write, you send it to where it is stored and all the copies of where it's stored. So it's moving all across the network. We say you should really have sub 1 millisecond latency. Otherwise, the system's just not going to respond. Now, there are timeouts in Hazelcast. You can adjust the timeouts for members pinging each other, and it's the wrong solution to change those things. If the ping time is slow, your network is slow, fix your network. So you need a good network for a communicating system. And at this point, I have to mention throughput and latency, because they're quite often confused. And people will say something, well, we've got a 10 gigabyte network. And what that doesn't move data faster than a 1 gigabyte network. You'd think it would, because it's like 10 gigabytes. It's like, what it means is it can move 10 gigabytes in the time that a 1 gigabyte network can move 1 gigabyte. So it's still got to move the same. So think of it like a waterfall. Your throughput, your 10 gigabytes, is how much water goes over the waterfall. When it rains, more water goes over, but it takes the same amount of time to drop, and that's the latency. So the data from A to B is the thing that matters. And if you're doing a lot of data volume, then the throughput's important as well. But it's the latency. Just a quick ping message might be small, but if it takes a long time to get there, then it's not much use as a ping message. And the thing we've seen is you don't get the network speed you claim. So, you might have a car that has a speedometer that goes up to 100, but, if you try and drive that in London traffic, you'll never get to 100 miles an hour, or because you've got arrested at 70 is the speed limit, but that's a separate thing. You never get that fast. The traffic chokes it. So what we've seen, a 10 gigabyte network card can deliver 10 gigabytes in a second, but it generally doesn't. We've measured things, and generally, you might get 7 gigabytes through a 10 gigabyte network. And that's like saying your car can go to 100 miles an hour, but you're only driving it at 70. And generally, that's not a big concern, but just a thing to be wary of. And where it matters the most is when you're doing that big data transfer. One of the things we do in Hazelcast is if a node joins the cluster or leaves the cluster, you rearrange the data you've got to balance it out. So that's like a huge amount of data you might be moving across. And if your network's slow, that rebalance operation to get the system back into tune takes time. And we've measured it that we managed to saturate the network to 20%. And it's like, well, the network could actually given us much more, but there's other things to consider, and they're moving the data. There's all the checkpointing and so on. But you need a good network, and it must never break. Now people talk about things like somebody's cut the cable, and it's like that never happens. Real networks are multi-virtualized, but what does happen is somebody deploys a firewall rule. So here's two Hazelcast instances, and there's now a firewall between them for some reason. The network's actually doing the right thing. It's appearing to have been cut in two, but it actually isn't. It's just not allowing traffic through. So it's not actually a fault. But the flip side is firewall rules can always be reversed. So it's often a lot easier than if somebody's cut a network cable in two, which, as we said, doesn't really happen. Modern networks have got multi-routes and all networking stuff that makes them nice. So just be careful. If you think you're going to move, 10 gigabytes across a 10 gigabyte network, you're not. It's just like a JVM. You can't put 10 gigabytes into a 10 gigabyte JVM. You've got to leave a bit of headroom. So your network needs to be fast, and it needs always to be fast. It's no good if it's kind of slow occasionally, because it's a shared network, and the other times there are like spikes. So the day you measure it, it might be fine, and then more applications may get loaded onto your system, and that slows it down, or the day you measured it wasn't a representative day. So just be a little wary of measurements. So just to summarize, faster than 1 millisecond latency, now and always. You won't get that actual speed, but it doesn't really matter. And everything's fine on the network until the day it isn't, which is back to our rule 4. Somebody's deployed a firewall rule, and your cluster is, impaired. So don't forget to plan for failure. So this is why we introduced these rules in this order. So rule 5 mentions rule 4, and rule 2 mentions rule 1. Did we mention rule 1? Rule 3's in there on its own, hasn't been mentioned yet, and I don't think it does actually in the later slides, but so don't forget rule 3.